Granular materials have path-dependent response to external fields due to the inherent heterogeneity of the contact force network and furthermore the resulting fabric of the microstructure. These heterogeneous materials exhibit irreversible deformations, and thus constitutive models need to incorporate temporal information. To model these materials, internal state variable theory provides a mathematical framework to incorporate features that contribute to the mechanical history of the material. One can then subsequently predict the resulting macroscopic mechanical properties such as strength and failure. In this framework, one utilizes an evolution equation to capture the path dependence and how these internal variables evolve, which can be written either as a function of stress or as a function of strain. This internal state variable theory has been used to model a variety of path-dependent materials, including polymers, biological materials like human bone, and metallic materials that exhibit plasticity. And the key question that I address in this work is whether we can use a multivariate probability distribution of contact forces and contact interactions of the granular material as an internal state variable in a continuum constitutive equation. To that end, we propose a generalized granular micromechanics approach, which allows one to upscale from the intergranular contact interactions, intergranular constitutive equations, to a representative volume element that captures the effective behavior of the system by capturing the statistics of all grain pair interactions, and then updating the stress tensor as a function of invariance of the deformation gradient. And in this presentation, we discuss how one could utilize M in a meaningful way to obtain both the microstructural statistics as well as macroscopic field variables like stress and strain. We now define a distribution of microstructural statistics M. M represents the distribution of branch vectors L that constitute all the grain pair contacts in our system. We consider an integration domain that is the subset of mechanical contacts that cause contact forces, which in the case of a monodispersed packing ranges up to 2 times the undeformed contact radius. We also define a normalization constant that represents the density of pair contact interactions, which is dependent on the evolution of the mean coordination number as well as the volumetric deformation given by the Jacobian. Finally, we define a constitutive relationship that allows us to obtain the stress over the entire assembly of particles as the expectation over all grain pair contacts, given a contact law that relates to displacements to the interparticle forces. We now discuss the different mechanisms of microstructure evolution. One key mechanism that is important to granular systems is the non-affine evolution of existing contacts. And what I mean by this is that in addition to the deformation induced by the global deformation gradient, there is also internal degrees of freedom associated with the microstructure evolution, causing internal rotations as well as other local deformation gradients that can then result in different deformation fields experienced by each grain pair. To that end, we propose a multiplicative decomposition of the deformation gradient into a global affine part and then a subsequent local non-affine part. One key point to make is that this is a departure from the Cauchy-Born rule that has often been used to assume that the microscale deformation of a system follows the overall deformation gradient, and we instead determine basically what the local non-affine field is as a function of the microstructure. Another key aspect of microstructure evolution is the evolution of pair contacts. And the way we examine the evolution of pair contacts is in terms of the volumetric deformation. And what we can see here is that when we apply volumetric deformation laterally and in the transverse direction, we find the formation of new mechanical contacts. And thus we sort of decouple these mechanisms where we have just the formation of pair contacts from point contacts as well as the non-affine deformation of existing contacts. Using those two mechanisms, we now show an overview of how to derive an evolution equation for M. we specifically propose two terms where each aspect is held static, namely one term that captures the non-affine deformation of the microstructure given a fixed set of contacts, and then another term that captures the evolution of pair contacts given a fixed global deformation gradients. The key assumption made in this representation of the evolution is that we assume that non-affine evolution occurs under a fixed density of pair contacts, and we will show the benefit of this assumption in the next slide. We now show the derivation of the pair contact contribution, and we see that it is a simple scaling of the evolution of pair contacts by a normalized version of the microstructure. We now derive the non-affine contribution to the evolution equation, and by assuming a fixed set of pair contacts, we're able to use the Reynolds transport theorem to then obtain that contribution in terms of the rate of L. We now show how to simplify the evolution equation by assuming the multiplicative decomposition of the branch vector L, which subsequently becomes an additive decomposition of rates, where we have an affine velocity gradient and a non-affine velocity gradient field that depends on the microstructure. We can then subsequently simplify the evolution equation by neglecting higher order gradients and absorb the rate of pair contact evolution to obtain a scalar evolution law that simply depends on the trace of affine and non-affine rates of deformation tensors. We now show some special results for the affine and non-affine terms. For the case of affine deformations, we find a specific expression for the non-affine term in our evolution equation that relates the normalized gradient of m to the evolution of pair contacts. We also furthermore see that for any loading path that the affine term reduces to the rate of relative density or the rate of the Jacobian, which is illustrated below. We now propose a possible solution to the evolution equation that takes the form of an exponential function in terms of a function kappa that is differentiable in time. We now apply this approach to the case of a monodisperse packing under die compaction. We specifically examine non-cohesive frictionless packings of approximately 40,000 particles with varying hardening exponents from results from particle mechanics calculations. We now show the predicted contact force distributions and the non-affine fields at two different relative densities for one of the example cases, particularly for hardening exponent of 5. One key thing we can see is that we can clearly see the dependence on orientation theta in the non-affine field, and we can also see that this approach captures the distribution of contact forces with high statistical significance. We can subsequently also predict the evolution of macroscopic field variables, which in this case would be the density of pair contacts, rho PC, the backwall tractions, which is the projection of the stress in the loading direction, and then the sidewall tractions, which is the projection of the stress tensor in the lateral cylindrical direction. And what we can see is that we get remarkable predictability of this model, assuming that we know the parameters of M. And we can then utilize the parameterization of M in the form of the evolution law to update the macroscopic field variables. And one key aspect is that we utilize a stress-free configuration as our reference configuration and update relative to that. In conclusion, we can describe the path-dependent evolution of granular systems in terms of a rate of generation of pair contacts and in terms of a rate of affine and non-affine evolution. We furthermore successfully demonstrate the implementation of this approach to the case of die compaction and explore the nature of the non-affine field through the parameters of M. Finally, we have generated a dataset of granular microstructures subject to different loading paths and next plan to explore the application of this approach to these cases. Thank you all for your attention.